Okay, everyone, welcome back. This is actually one of the hardest homework assignments of the year, and it was just one of 9 things you had to do this week. This is the homework on the pumping lemma. And we did one of these, well, I almost did it in class, but we did it on a video that I recorded, which you watched. And I think that description was extremely thorough, so hopefully you're okay, and you get it. And now we're just going to do 4 more of these, and I think 4 was too much. I think 3 was enough. So I'm just going to do the first 3, and just don't bother doing that last one. Alright, and what I pushed very heavily on the video, because I'm a high school teacher, is that I think for clarity and structure, I would like to institute a sort of uniform standard in which we very clearly explain what we're doing, and so I made sort of like a 10-step program for doing one of these pumping lemma proofs, and I'm going to stick to that format, and I think you should too. Okay, so step 1, introduce your language. Okay, so here we go. So I'll even call this step 1. Let C be the following language. Well, this is just the language I gave you. It should be all the strings with an equal number of A's and B's. So W, where W has an equal number of A's and B's. Okay, so this is similar to, but different from, the one example we've done already, which is strings which had an equal number of A's followed by an equal number of B's. Now more generally, the A's and B's can be whatever order, but this language just can't be regular. And well, why not? I guess the answer is that a finite state automaton simply just can't remember how many A's and B's have occurred so far. And so if your string is extremely long, you know, thousands of characters long or something, then the only way for the machine to know whether to accept that string is to somehow keep track of how many A's and B's there are, and the machine just sort of can't do that. Okay, more on that later. We are going to prove that this language is not regular, and we're going to do it by contradiction, which is how the pumping lemma is generally used for this purpose. So here we go. Now we explicitly assume, for the purposes of contradiction, that this language C is regular. So suppose C is regular. Okay, this is going to lead to a contradiction way down here. Okay, next. Well, next we just apply the pumping lemma. Okay. And the pumping lemma is a theorem that applies to all regular languages. And so on the assumption that this language C is regular, I can apply the pumping lemma to it. And here I think we are just going to basically just regurgitate the pumping lemma, which I think is of value. So well, what does the pumping lemma say? I'll just say it right now. By the, it's very loud, by the pumping lemma, there exists some P, the pumping length, such that for all strings, okay, so for all strings in C that are longer than P, they can be partitioned. So for all strings in C, if the length, for all strings S and C, if the length of S is greater than or equal to P, I think it's greater than or equal to, right? Yeah. Then S can be partitioned into 3 substrings, X, Y, and Z. Yeah, Theo, substrings. But there exists some P, the pumping length, this is just a number, such that for all strings in that language, if the string is longer than P, then the string can be partitioned into 3 sections such that those 3 sections have certain properties that basically, yeah. Well, okay, the middle can't be 0, so the length of the middle section, what? didn't really prepare much for this lecture, is greater than 0, yeah, here we go. And also that the first 2 sections are completed. Thank you. That the length of the first 2 sections together, this video is getting all much better now, is less than or equal to p, and also the sort of important part, maybe this horizontal thing is kind of distracting, such that okay, I'm back. Every string longer than p can be partitioned into these 3 sections, such as the middle section is sort of non-empty, you know, that string is non-null, so to speak, that the first 2 sections occur in, have length less than or equal to p, and the important part is that x, y, I, z is in C, sort of for all I greater than or equal to 0. Okay, so what's going on here? This is like as promised. This is just the regurgitation of the pumping lemma. And what does the pumping lemma say? It's a theorem that applies to all regular languages, and it refers to all strings of that language which are larger than the pumping length. We don't need to revisit the details of the proof, but remember the inspiration of the proof of the pumping lemma was that p, the pumping length, is in fact the number of states in a finite automaton which recognizes this language. Okay? And I think it's helpful when using the pumping lemma to still have that kind of intuition and understanding. And basically what this is saying is, dude, when you process a very, very long string, if the length of that string is longer than the number of states in the machine, then we have to revisit some states in some kind of loop, because there are only p states, but our string is longer than p, so some state must be visited twice. And if a state is visited twice, then there's sort of the part of that string and then accepted. Then there's the part of that string which is processed before we hit that state. Then there's the part y, which is processed as we loop from that state back to itself again, and then there's kind of the part at the end. And so what this says is that there's some legit looping piece, there's some sort of piece of the string which is processed in between the 2 visits to that state that must be revisited at least twice, and also that that whole thing has to happen before p, because there are only p states. So so the loop must occur in a piece of the string which is, the part before the loop and the loop have to be fewer than the number of states, because for the same reason that we just said. If not, well, because we only have a certain number of states, so, okay. It's just the pigeonhole principle applied to the number of states. But then, of course, the intuition is maybe a little tiny picture is worth it, since we are supposedly going over this homework. Although I thought the video was quite good. So there's some start state, then there's some state, then there's some accept state, and there's some there's some state which gets visited there's some state which must get visited multiple times, and that must happen before p, because the machine only has p states. And so this is kind of the general gist. So what is x? X is the piece of the string that gets processed before we hit the repeat state. Y is the part of the string that gets processed in between, and z is the rest. This is the whole thing. Going way too slow. The real content of the pumping lemma is this one, which says, well, we can now sort of pump this string, and if y is a substring of s processed in between the state and itself, then the machine never knows what's happened in the past, and so any string of the form xyyz or xyyyz or even just xz must also be accepted by this machine, and therefore must also be a member of the language. notice that the pumping lemma itself doesn't refer to machines because we've sort of abstracted away from that, and it's just a theorem about regular languages, but we use the machines to prove it. Okay, maybe that wasn't necessary, all that long-winded ramble. Let's push on with the proof. What's the very next thing we do? The very next thing we do is the hardest part of all. It's the part that requires you to actually do some independent, creative thinking mathematics. It's not algorithmic. You have to come up with a string. After all, this is a proof by contradiction that we're in the middle of. So in order to execute the proof by contradiction, you have to sort of catch the pumping lemma breaking. And so to break it, you have to access sort of intellectually and emotionally or something like that, the essential non-regularity of this language. Why is it fundamentally that this language is not regular? And the answer is because we can't remember how many A's have occurred and how many B's have occurred. And so we can sort of, on the assumption that this language is regular, we can sort of break it by just taking a very, very long string. And in particular here, maybe it's clear that the exact same counterexample from the one we did on the video is also going to work. If P is the pumping length, which we informally think of as the number of states of the machine that accepts every string of this language, then if I just make a string that's so long, A to the P, B to the P, then this machine just can't, this machine just can't remember when processing this string how many A's and B's have come, because there are only P states. And so by the time I get, I try, how can I put this? I think this is clear. So by the time I've processed the first half of this string, I've already used up all the kind of states of the machine, and there are none left. So here we just say, consider this string. That was what I called step 4 in the video. I think just to introduce your string. And your string is always going to be in terms of P, because we introduce the language, we suppose the language is regular, we apply the pumping lemma to that language. The pumping lemma says there's some pumping length P, and now in terms of P, we introduce a string. And what's clear about this string is that it's in the language. So that's important to the whole point, is that we're coming up with a string in the language. And is it in the language? Well, yeah, it just is, right? Because it has the same number of A's and B's. So just note that explicitly, that R is in C, by the definition of C. And R is long, which is important. R is a long string. What is the actual length of R? It's 2P, which is certainly greater than or equal to P. So the pumping lemma applies. It applies to all strings of this language which are sufficiently long, and this is one of them. Okay, that was sort of point 6. Now, by point 7, now having established that this string R meets the preconditions of the pumping lemma, it's a string of the language and it's quite long, I say, this string R must consist of 3 substrings X, Y, and Z. I'll just write meeting the conditions above. Meeting the conditions above. I don't think we need to actually rewrite the whole thing again. Okay. Good. La 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 la. Yeah. All right. And now we have to. Okay. This part should be sort of easy, because I think coming up with the string, the correct string, is the hard part. But where does the contradiction come from? Well, if this string can be broken up into 3 substrings like this, what do we know about those substrings? So let's sort of perform an analysis on X, Y, and Z. Well, I guess the key thing is that X, Y has to be less than or equal to P. So, So since X, Y is less than or equal to? Yeah, less than or equal to P, and the first P characters of R are all A's, then I basically know that, okay, well, what's going on here on a deep level is I know that I have to sort of already loop before I hit the pumping length P. And so if I'm already looping, if I'm already doing the lead up to the loop and the complete loop happens before we hit P states, as it must, then it must be true that, well, okay, hold on, I'm going around in circles a little bit. Yeah, so, let me just finish that sentence. Since I lead up to the loop and I complete the loop before the string is P characters long, and the first whole P characters of this string are A's, then in fact it must be the case that the entire X part and the entire Y part consist of A's. It's confusing because this is a proof by contradiction, so sort of none of this can happen, and I think we're gonna sort of see that now. Are all A's. So continuing this analysis, so X and Y consist entirely of A's. X and Y consist entirely of A's. And hopefully you appreciate that that's just not possible. Why is it not possible for X and Y to consist entirely of A's? Because if Y consists entirely of A's, then this same machine should accept any number of applications of that loop. And so it means we can now pump. And so that's what we do. Step 9 is the pump step. This is just what we call pumping. I think I'm doing this right. We say, okay, oh, and wait, so let me just, for purposes of clarity, I'll just say, if X and Y consist entirely of A's, let's say that that Y has M A's. So just let M be the number of A's in Y. M is just the length of Y. The length of Y is just M, and they're all A's. Okay, and now finally we pump. We use the point 3 of the pumping lemma, which says that if this string is a member of the language, then so must every string with any number of Y's in it. So now we say, by the pumping lemma, sort of like number 3 or something like that, I'll just say by the pumping lemma, other strings must also be members of this language. In particular, I choose x, y squared, z. And here I assert that this string is a member of the language by applying the pumping lemma. So I guess there's still some sort of creativity, because you have to choose the string that breaks it, but you also have to choose the sort of another kind of counterexample string, which the pumping lemma will sort of assert. Well, you have to find the string to pump, and then you have to know what to pump it to. Okay, so by the pumping lemma, this is language, but of course, this is just not a string of the language, right? Because did I make this like a separate thing? I guess I didn't. Maybe this should be point 10 or something. But because point 10 is but an analysis of x, y squared, z means it can't possibly be in C, because what is x, y squared, z? X, y squared, z is going to consist of y had m a's in it, and now I have just added another y. So x, y squared, z is going to have m more a's than r did. And so in fact, I can say that this string x, y squared, z is in fact a to the p plus m, b to the p. But that is just simply not in C, by the definition of C. This is a very, very clear, thorough proof. And so on the one hand, we have that x, y squared, z is in C, but on the other hand, by just looking at the string and analyzing it and looking at the definition of C, we see that the string is not in C. Therefore, we say contradiction, and so C is not regular. Okay, that was way too slow. I was a little bit rusty on this, and I had a baby distraction, but good, hopefully you watched on 2 times speed. Let's do 2 more that get harder, and now we'll go faster, because I'm more on this now. Whew. So I think this is pretty hard. This is like some advanced college level theoretical computer science, but with a high school level of telling you what to do or something. Okay, good. Next language is this language D. So what did I say? Introduce the language. Okay, so take language D, which is all strings of the form a to the n squared, where n is greater than or equal to 0. Okay, so now we have a unary alphabet. This alphabet consists of only 1 character A, and we're basically, in words, this is just the set of all strings from this unary alphabet, which are a perfect square, have perfect square length. Okay, so we want to accept, 5 A's and not 5 A's, sorry, 9 A's and 25 A's and 100 A's, etc. But if it has 17 A's, then it's not a member of this language. Well, perfectly coherent language, but this language is not regular. And I shall prove it. Suppose that D is regular. I maybe could have just, well, too late. Suppose D is regular. Okay, step 3, regurgitate the pumping lemma. I'm going to do a better job now. By the pumping lemma, there exists some P such that, the pumping length, such that for all S in D, I guess I'm not 100% regurgitating the pumping lemma because I'm applying the pumping lemma to sort of my particular language, D or something like that. Anyway, on the assumption that D is regular, by the pumping lemma there exists a P such that for all strings in D, if the length of that string is greater than or equal to P, then that string can be partitioned into 3 substrings, X, Y, and Z, that satisfy the conditions of the pumping lemma, which is that 1, Y is something, 2, the whole XY piece occurs before P, or has length less than or equal to P, and also the important one, that X, Y, I, Z is a member of D for any I greater than or equal to 0. Okay, introduce your language. Suppose it's regular. Invoke the pumping lemma. Now, we have to find a string which captures the fundamental irregularity of this language. And okay, maybe it's just obvious, or maybe it's not, but right, we just can't recognize this language. If you try to make a machine to do it, well, your machine can only be so big, right? So if your machine has 1,000 states, well, okay, but there are perfect squares which are way, way bigger than that. Yeah, in fact, the gaps between a perfect square and another perfect square can be sort of arbitrarily long, right? So once you take, let's see, is that true? Yeah, once you give me like 1 billion, let's see if I'm doing this correct. 1 billion squared is whatever it is, but 1,000,000,001 squared is a quite much bigger number. It is 2,000,000,001 bigger than 1 billion squared is. And therefore, the gaps between consecutive perfect squares grow up to infinity. In fact, they grow linearly. And so, we can, if this machine is to accept arbitrarily long strings, then you need a sort of infinite amount of memory or something like that or an arbitrarily large amount of memory to keep track of how many A's you've seen so far, and that's just what we can't do. Okay, I think that's a good explanation. And so what's kind of like impossible? What's impossible for this machine to do is to keep track of how many A's it has encountered, sort of like since the last perfect square or something like that. Okay. Yeah. And so, given some p, I think the string which will break it is this one. All right. Consider r equals a to the p squared. Okay. So this string is going to have p squared number of A's in it. Okay? Well, what am I supposed to say about this string? Here I had to just come up with this. This is what makes these proofs hard. There's some amount of, besides the complexity of the pumping lemma and the logical structure of the argument, and besides just the fact that proofs are hard, you have to come up with this string yourself. Okay, and well, why is this string a good string to consider? Because, first, certainly, R is in D by definition of D, because, yeah, it has a perfect square number of A's, it has p square A's. What else is good about this string? Well, it's very, very long. The pumping lemma applies to very, very long strings in D, and in fact, the length of R is p squared, which is in fact bigger than or equal to p. Okay, so the pumping lemma applies. And now, what do we do next? Oh yeah. Okay, so now what does the pumping lemma say? It says, okay, so by the pumping lemma, having established that this string R is both in the language and very long, it must be partitionable into these three regions. So by the pumping lemma, R looks like x, y, z, or R can be partitioned into the form x, y, z, such that x, y, and z satisfy the conditions above, which I don't think we need to rewrite those three conditions. Okay. And now we sort of perform an analysis on this string. Well, here it's maybe, what am I writing here? Yeah, right. So, okay, so here it's actually somehow it's a little bit simpler or something because all the characters are just A's. So what I know is that y is something greater than or equal to 0. So okay, maybe I'll just say since the length of y is greater than or equal to 0, let for purposes of specificity, let's let the y be of length m. Okay, where m is greater than or equal to 0. No, greater than 0. Greater than 0. Okay. So what that means is that this string R has been broken up into three pieces, x, y, and z, and there are precisely m A's in the y piece. Okay, well, that is a problem. Oh, and I also know, sorry, I forgot to say this. I should just probably look at my notes. Y is greater than x, oh, okay. Yeah, also, and here I think is where this becomes important, maybe. Well, we've used this already. I also know that the lead up to the loop and the loop all happen before p. So also xy is less than or equal to p. So if xy is less than or equal to p, then certainly y itself is less than or equal to p. Remember, x could be 0, but if the two of them together has this length or less, then so does this piece have that length or less. Okay, and so what we conclude from the previous two steps is that, in fact, this number m has to be somewhere between 0 and p. Okay, this is kind of dumb, but this is a formal proof, so I'm being very explicit about every single little thing. The length of this loop is something greater than 0, but also less than or equal to p. Okay, that becomes relevant now because well, now I just pump, I guess, right? So that was my analysis. Now let's do the pumping. So when we pump, and I think it's clear here that if I just pump once, as people say, then I have a string which is not in this language. In other words, make this machine sort of process that loop y one more time. So now I'll say by the pumping lemma, I now introduce a new string, which is the string x y squared z. And it must be a member of D. That's what the pumping lemma says. And yet, but what is this string x y squared z? Well, it in fact, since y has length m, in fact this string has m more a's than r does. Therefore, this string in fact is just a to the p squared plus m. Because I just added m a characters there to the length of r. I think it's pretty clear, but slow. Okay, what's wrong with this? Well, what's wrong with this is, hold on, I need to make some space or something. So I'll just squeeze in here. Of course, this was meant to apply to, for any I. Okay, what's wrong with this? Well, what's wrong with this is that this string x squared z is the pumping lemma is telling me that it's a member of this language, but of course it just isn't. And why isn't it? It isn't because this is just not a perfect square. So maybe like in a different color, sort of like lemma or something. And in words, what this lemma is saying is, dude, if you take a perfect square, this is just a fact of numbers now, you could possibly just cite this without proof, but if you take a perfect square and you add to that perfect square, a perfect square of the form p squared, and you add to it a number which is less than p, that's just not a perfect square. Okay, and so here we go, right? If you give me this m, let's see, how do we do this? I guess I'll just add p squared or something to all three sides of this inequality, and so we get p squared is less than p squared plus m, which is less than or equal to p squared plus p. But also, of course, p squared plus p, right, small here, is less than or equal to p squared plus 2p plus 1. Because I've just added p plus 1 to, well, it just is bigger, right? This side is p plus 1 bigger than this side, and p's positive. Okay, so by a kind of a transitive property here, I get that this p squared plus m is in fact between p squared and, do I get to